Okay, so let's take a look here. 17 is similar to one that we worked out yesterday in class, but definitely not the same. Okay, so 1 times 3 times 5, dot, 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 to 2n minus 1. And I would assume we're going to use ratio test. Have you tried that? Was it Alyssa asking? I forget who asked. It might have been Grace. Oh, here we go. Okay, now I gotta wait for the little X and then close it, okay? Ah, this keeps cutting out. 2, 5, 8, dot, dot, dot. 3n minus 1. Okay. This is definitely just gonna keep doing this like they're not here and then they're here for a second. I'm so sorry, you people. This is gonna get annoying for you, I'm sure. And if you just want to watch a recording later, I am fine with that. I'm not planning on doing crazy attendance, okay? But it's kind of entertaining maybe for you. Maybe not at all. Okay. So I'm going to look at the ratio test, I think, for 17, just because there was one similar to this in that chunk of homework before. So we've got our a sub n is this, and then a sub n plus 1 is what I'm going to work on. No, but someone's door keeps squeaking. I think it might be Mrs. Lester's. Well, and with it being so like rainy and stuff too, and to cut the humidity, a lot of times you use like air conditioning, and it's probably a little crazy to use that right now. Okay, let's see here. Okay, so we got 2n plus 2 minus 1. And if we look at these, they're going up by 2 each time. So if this goes down by 2, the term before it would be just this gone, which would just give us a 2n minus 1. There we go. Okay, so that's the top. And then the bottom. 2 times 5 times 8. Okay. Yeah, it's out. I had it long enough to say, this might get really annoying, and you might just want to watch this recording later. And literally, I'm recording right now. This is going to be a good one. 3n. No, you're fine. I'm not like, I don't care. They don't care, you know? It's good. Okay, these are going up by 3 each time. So if we go down by 3 to get the one before, it's just going to be 3n minus 1. Whoops. That's good enough. Okay, and then if we're using the ratio test, we'll do the limit as n goes to infinity. And I do this one first. Let me get rid of this extra writing. And then I multiply by the reciprocal of the a sub n, because I'm dividing by it. And this is going to cancel real nice here. Okay, so the reciprocal of that would put this 2, 5, 8 stuff on the top. And the 1, 3, 5 stuff on bottom. Okay, and then this here cancels with this here, and this is canceling with this. So all we have left then is the limit as n goes to infinity. And if I multiply that through, because it's probably just easier, we got 2n plus 2 minus 1 would be plus 1. And then 3n plus 3 minus 1 would be plus 2. And then if we try, I'm just trying to connect with you guys again. Then if we divide everything by n, we just get 2/3. And it's greater than 1 or less than 1. So with this one, it's going to be less than 1, so it's going to be convergent by the ratio test. Okay, and then 19. Okay, it's letting me preview. I'll just write it. I'm going to write 19 down here. Okay, so this is the one you needed, Claire. N equals 1 to infinity. Let me think here. Did you try anything yet?
No, because every time I looked at it, I just kept getting like the natural lows and all that.
Yeah.
So I was like, I'm not really able to.
Whenever I see the -1 piece, I'm always gonna be like, well, I don't know, I would maybe try the alternating series test. I don't know that that's gonna be what we need here, but it's like the internet just keeps kind of being there and then it's gone. I'm gonna try to close it and try again. It's gonna be like the most annoying recording of all time. Oh well. Okay, so if we try alternating series, I'm gonna look at like I like to look at part double I a lot of times before I look at part I, because right away I'm like, I don't know if that's getting smaller just by, you know, glancing at it. So I'm just kind of glancing at the part double I. And my b sub n is natural log of n over square root of n as n goes to infinity. Okay, so this I would get infinity over infinity, so I'm going to do a L'Hopital situation here. And natural log of n would just be 1 over n. And then this is going to turn into 1/2 n to the -1/2. And then I would probably move both of these things to the top. Like dividing by 1/2 is the same as multiplying by 2. This is the same as moving it to the top and just having a square root of n. But then what this does, the 1 over n, is it's going to put an n down here. And then we can clean this up by canceling the square root of n out or subtracting the exponents, however you think about it. So this is going to be the limit of 2 over square root of n. Does that all make sense? And then if we go to infinity, this does go to 0. So if part double I works, it's worth it to like look into part I. Do you see what I'm saying there?
So it's not part method, it's just getting rid of it.
Yeah, like this is 2n to the 1/2 over n to the first. So we just subtract those exponents. Do you see what I did there? It's only heart method if you have something like this. Yeah, with like 2 terms up there. Nope, that's okay. And that's usually how I kind of do it, as I circle it there. Okay, so part double I works, so I'm going to try part I now. So our b sub n is obviously what's right there. Natural log of n over square root of n. And b sub n plus 1. So the numerator is bigger, but the denominator is also bigger. So what I would probably do is maybe jump to my calculator and see which one is bigger because it's not super obvious. Now you might not have your calculator on the AP test, and if that would happen, I would probably be like, well, part 2 works and I'm running out of time, so I'm going to say convergent by this, and I would just like state part I if I needed to. But I'm not sure if it'll work. Let's see if it does. So in my y1, I'll put my b sub n. And then my n plus 1. Square root. Okay, I think I typed this right. So now if I look at my table, that's what I was wondering, yeah. So we want, for this to work, we want this one to be smaller, right? The second one that I have in here. And it's like eventually smaller.
Actually smaller at first.
Yeah, because here it's like they're starting to meet up. I see what you're saying. But then you can see that, yeah, eventually smaller does work. So I feel like we can say that it is by the alternating series test. But it wouldn't be like for all n. It would be like eventually kind of situation.
You have to say what?
Yeah. So 27, we'll talk about how the book does it because a lot of you will probably be checking the key trying to figure out what they did anyway. And I think it's important to like see different ways to go about doing some of these. What I tried first, and I tried this because I've seen it like work before, is I tried to do a comparison test, and they did do a comparison test, even though it may not look like it when you check the key right away. But I tried a comparison test, and the reason I tried a comparison test is because I can see the denominator be like k cubed, and the numerator is like k natural log k. Okay, what can I do with that? And that's actually what the book used to compare it to, was k natural log k on top, and then k cubed on bottom. But then they had to do an integral test to see if that was convergent or divergent, to see if the comparison test was conclusive. Like, it's a lot of work for a comparison test because it's not a p-series and it's not a geometric series. It's, you know, an integral kind of thing. So we will do it that way, but I'm going to show you how I went about doing it because this is where my brain went. So the denominator for comparison here would obviously be k cubed. That's the dominant piece down there if I multiplied all of that out. Now the numerator, I was like, okay, I want to get this to be like a p-series or a geometric series because it's way quicker that way. But I can't just say it's k because it's k times something. And when I compare these two just like right off the bat, let me write the a sub n here. I notice that this denominator is bigger, right? So I want it to be that my inequality goes that direction. So if I want it to be my inequality is going this direction, and I want to assign something for this numerator when this numerator is this one's going to have a bigger numerator for me to feel like confident that the inequality goes this direction. Does that make sense? Like if this denominator is bigger and this numerator is bigger, for sure a sub n is less than or equal to b sub n. So then I was thinking about this because I think I've seen it before in a problem. Like the natural log graph, we know the natural log graph looks like this kind of a thing, right? And we know the graph of just like y equals x, or the graph of k in this case, would look like this. Isn't k going to be larger than the natural log of k? Like for any value that we pick there. So what I did is I replaced this natural log of k with a k, and I said, okay, my numerator is going to be k squared. And this is where I started. So then if I reduce that down, it's just 1 over k. So would this be convergent or divergent? Divergent. But if it's divergent, we don't know anything about this one. So I went, man, I really thought I had it. So then I was going, okay, well maybe if I lower this a little bit. So instead of k squared, I make it k to the, and I did 3 halves because halves are, you know. But even if I did like, let's say 1.9 or something, I still feel pretty confident that this one is going to be bigger than this numerator here. Or I could even do 1.99 for all I care. You know, you can make it pretty close to 2, and I still feel confident that that's going to end up being above the other one without like having to go to my calculator. And I did end up using 3/2, and then I went to my calculator and compared the 2 columns in my table, and it worked. But even if we did this, when I reduce this down, this is just going to be 1 over k to the 1.01 or 1, depending on what you use for that numerator. And if we look at that p-series test, if p is greater than 1, it's going to converge, right? So then I know that this one here converges. And so a smaller one is also going to converge by the comparison test. It's a lot easier, but it's a lot harder. It's like we're not showing a lot of math there. This would be if I was doing a multiple choice, and I would kind of write it like this and be done with it. What they do, and there's a lot of value in what they do, so I'm not going to like cut it short of like being a valid way to do it, because theirs is much more sound probably. It just takes so long that I don't think we'd have time on the AP test to like go through all the steps, unless maybe it was a free response question. And if it was a free response question, you'd probably want something a little more mathematically sound. So what they do is they compare it. Our a sub n is still this, and our b sub n, they leave the numerator just like it is, and they make the denominator that k cubed, which is pretty obvious if we've done some of these, right? And then you can reduce the k's, so it just turns into natural log of k over k squared. And then they say, okay, I'm going to try an integral test on this. And if we do an integral test on this, we end up having to use by parts. And what happens if you get all the way through that integral is this one ends up being convergent. And because this converges, then we know that this also converges. So, I mean, it's the same idea. It just, that integral test with it being by parts is kind of long. But if anyone wants help with that later, just make sure you ask on Friday.